Welcome to Strength of Materials. Last term we talked about force, which you will recall is external stuff, in our structures class. And that force was acting on the outside of rigid bodies that are not moving. This term we'll talk about stress, which is internal stuff that happens inside in response to those forces. So let's think about stress. It's all related to one of the great intellectual discoveries of history, which was the idea that all material acts like springs. All material is elastic. And that is true of all material, not just rubber and foam, but it's true of steel and concrete and plastic and anything else. All material is elastic. And you can think about this as a kind of like springs. So this picture here is a metaphor for atoms connected by atomic bonds. They're chemical bonds, which are, of course, they're electrical bonds. So each one of these marbles represents an atom, and the springs represent those electrical bonds holding the atoms together. If you compress something, those atoms get squeezed closer together, like if you're standing on the floor. Then when you step off of the floor, those atoms spring back to where they were. If you hang a weight from something, those bonds between the atoms get stretched out, and when you remove the weight, they spring back to where they were. Force acts on the outside of a thing. It's a push or a pull. And stress is what happens inside as a result of that force, and that's what we're going to talk about this term. You can think of it as a measure of intensity, or how hard those atoms are getting pushed together or pulled apart. So force is external. It's measured in pounds if we're using the US system. Stress is internal. It's measured in pounds per square inch, PSI. And I use that phrase PSI as a memory device to help me remember how you figure out stress. You know, if you look at a bicycle tire or a wheelchair tire or a car tire, it'll have letters on the side that say inflate to so many PSI, pounds per square inch. That's what PSI stands for, and that can help us remember what we're talking about. So here's the formula. There's a letter sigma. We'll use that to stand for stress. Stress is pounds per square inch. It's force over area. Pounds per square inch, or PSI. Some books use a different symbol. Some books, including our textbook, use this squiggly thing. It looks kind of like a flattened letter S or a letter F. It actually is also a Greek letter sigma. In Greek writing, this thing that looks like a flattened S is a sigma that you use on the end of a word, and this thing that looks more like an O with a tail is the general sigma that you can use any place in a word. So they're both sigma. I prefer to use the one that looks like an O with a tail because for me that flattened squiggly one looks too much like a different letter, like maybe F for force. So I don't want to get confused. So we're going to use the round sigma. Also, up until now, our book has been using capital F to stand for force. Now they're going to start using P to stand for force. Don't ask me why they do that, but people do that. I think of P as standing for pounds. So stress is pounds over square inches. Let's think about how we can use that to figure something out. For example, here's a 100-pound weight, and it's hanging from a 1x1 square bar. Let's figure out how big is the stress in that bar. And we know that stress is PSI, pounds per square inch. So the 1 by 1 bar, 1 times 1 is 1, that bar has an area of 1 square inch. How big is the force? It's 100 pounds. So if we plug those numbers into our stress formula, force over area, we find out that the stress in that bar is 100 divided by 1. The stress in that bar is 100 psi. Now what if we hang that 100-pound weight from a bigger bar? We'll hang it from a 10-inch by 10-inch square bar. How big is the area in that bar? 10 times 10 is 100, so the area is 100 square inches. How big is the force? It's still 100 pounds, so our stress is now 100 pounds divided by 100 square inches. Now the stress is 1 psi. 100 divided by 100 is 1. This is the reason we put footings under our buildings, to spread out the force over a bigger area. And it's the reason we use snowshoes. So let's think about a boot, somebody's boot. Let's say this person weighs 200 pounds and they're walking across the snow with their boot. And I just took a random boot and measured it and found that particular random boot was 65 square inches. Okay, now how about a snowshoe? I looked in an LL Bean catalog and measured one of their snowshoes, and it appeared to be 600 square inches, so I'm going with that. And now just for comparison, what about a high heel? A high heel, if it is a 1/4 inch by a 1/4 inch, that would give you a 1/16 of a square inch. So we got 3 different sizes of areas. If you take the 200 pounds and spread it over 65 square inches, you get about 3 psi, 3 pounds per square inch, falling through the snow. If you spread that 200 pounds over a snowshoe, you have only 1/3 of a psi, 1/3 of a pound per square inch. If you take that 200 pounds and you concentrate it into that little tiny heel in the high heel, suddenly, go ahead and do the math with your calculator, 200 divided by 1/16, you'll get 3,175 psi. You can see why landscape architects and other people who do paving are really concerned about damage to concrete paving outside of restaurants and convention centers and so forth, where people might be wearing these sharp heels, because they can really put a huge amount of stress on the paving. Even if you have a tiny person who weighs 120, that's still 1,920 psi. So you can see the point here is area makes a big difference. Sort of an inverse of that, that's the same reason a thumbtack works. The thumbtack is kind of like a high heel. So you take a small force, but you put it concentrated in a little tiny point, you wind up with a lot of psi, and your thumbtack can go through paper or whatever. Remember in structures class, we talked about how there were 2 kinds of force, push or pull, compression or tension. That's it. In the world of stress, there are actually 4 kinds of stress. So you can still have compression, compressive stress. You can have tension, tensile stress. There are 2 other kinds. You can have shearing stress and torsion. So tension, tensile stress, and compression, compressive stress, act on if you think of a flat surface, a plane inside this column here, that's perpendicular to the direction that the force is acting. Shear acts parallel to the direction the force is acting. And don't worry about that if that doesn't feel right to you. Just remember, shearing is kind of like what happens if you take a pair of scissors and the blades are sliding past each other. You can cut a piece of paper with them, with the shearing stress. torsion is twisting stress, and we are not going to talk about torsional stress for the reason that it gets a little bit more complicated mathematically than we would like to dig into in this class. I can't remember how much our book goes into it in detail, but trust me, it's a little bit more complicated, so we'll just say, yeah, that's nice, and we'll move on to our compressive, tensile, and shearing stress. So there you are.